almost every year brings something new and exciting to explore. Some of those things will fade away, and some will end up impacting the whole industry. For the development of classical computers, the ones that we use every day in our everyday lives, games has had a big role. The flexibility of the form and the playful creative spaces that games can hone create a perfect platform for exploration and innovation. We might very well be on the verge of a new revolution in information technology. Quantum computers might sound like sci-fi, but they are already knocking the doors of this reality. Today's topic is quantum computers and games, and we have a pioneer of that field here today to give a lecture on the topic. So welcome to the stage, Dr. Wootton from IBM Research.
Thank you. I assume that I'm being sufficiently amplified. So yes, I'm James Wootton from IBM Research. Although a lot of the things that I'm going to be talking about today were also developed in my previous job at the University of Basel. So I'm not here to give you a sales pitch from IBM. I just happen to be at IBM, and I'm going to be giving this lecture. So at the bottom there, I've got some contact details where you can find me, and maybe the best one to highlight, if they're not big enough, is that on GitHub, I'm called Quantum Jim, and if you go there, then you can find the slides, and then anything you can't see on the screen, you can see on GitHub. So I'm going to begin by telling you about how we are going to be, I'm going to begin by talking about what games will be like for tomorrow's quantum computers, so for the quantum computers in a future era, because really quantum computation comes in various eras at the moment. We've just gone through the era where quantum computation was just something that people were thinking about, and now we're in an era where there's actual prototype devices online that people can play with. Hopefully in the next few years we'll get to a point where quantum computers can do things that normal computers can't, because at the moment quantum computers are sufficiently small that they're quite easy to simulate. So anything you can do on a quantum computer, you can do on a normal computer just by simulating it. But in a few years we should get to a point where quantum computers can do things that normal computers can't. But even so, we'll be in a sort of a strange regime where things are a little bit smaller and dirtier than we really want them to be. Because in previous years, scientists working on quantum computing have come up with some great algorithms that can run on those devices, but they've always assumed everything is very big and very clean, so they can get nice mathematical proofs. But in the next few years, we'll be working more down at the nitty-gritty of the hardware, and we'll be having to develop new ways of getting all of the performance we can out of the devices. And then in the far future, we will have everything big and clean, just as a mathematician dreams of, and we'll be able to use the algorithms that have been developed over the last few decades. So in this section, I'm going to tell you about some of those future eras where we have the ability to do things on a quantum computer that we can't do otherwise. And I'm going to mix together a little bit about the two future eras that pertains to. First, I should probably tell you what a computer is. I assume you all know what a computer is and have seen one, and perhaps even used one before. But I should probably give you a little bit of an idea about what sort of level we program quantum computers at, so that you can start getting into the mindset of how you would use these devices. So a computer is basically something which takes in information and spits out information. In the middle, it does some processing. So typically our digital computers, that are the ones we use, take in information written in binary. They spit out information written in binary, and in between they do things to that binary. And originally this was designed to solve mathematical problems, so you'd put in your binary that goes in would specify some maths that you want to do, and your binary that comes out would specify the answer. But we can also do them for other stuff. We could use them that your input specifies some button press on a controller, and your output specifies some character doing something in a game. So there's various ways we can use computers, but basically at the very lowest level, what a computer is doing is looking at the bits that come in, and usually looking at them 2 bits at a time and doing some comparison of those bits. So for example, that you could use the NAND gate. So a NAND is a very simple operation. You can think of it as the very simplest kind of computer. You give it 2 bits and it gives you 1 bit, and that bit tells you if at least one of the inputs was 0. So if at least one of the inputs is 0, it outputs 1 or true, otherwise it outputs 0 or false. And this is a very special operation. It may look very simple, but with these you could do everything. Everything that any computer ever does, any possible way of taking an input and running a program on it and spitting out an output can be written as a whole bunch of these NAND gates. So you can think of it as like the fundamental building block of computing. The way we actually implement computing, we use transistors typically, and you can't really explain what a transistor does very well in terms of binary, but you can build a NAND gate out of 1 or maybe 2 transistors. And you can even get chips which implement these NAND gates. So if you want to hardwire your program, that you set a load of voltages on one side and read a load of voltages on the other, and you can just get a few of these chips and wire them together. So this is the very most basic level at which you can do programming. It's not the level at which we do programming at the moment. When we want to add 2 integers, we don't go and specify all of the NAND gates that need to be done to add 2 integers. We just add them. We work at a more abstracted level now. Although if you look at early history of games, so even at the NES era, people were working far more at this sort of level than people do now. So yeah, anything can be compiled into a bunch of NAND gates. This is an example of how to add 2 bits. So it's the most fundamental level, and you can, if you want, program at that level. Well, now we've worked out the fundamental building block of computation, we can talk a little bit about computational complexity. So I don't want to give you a lecture in computer science here, but just to motivate what a quantum computer is and how it's different from a normal computer, we have to look a little bit at the notion of computational complexity. So a computer can do basically solve any problem, but the amount of resources required to solve different problems is different. And it depends on the nature of the problem. So for example, adding 2 numbers. When I was at primary school, they taught us that you write out one number, and then below that you write out the other number, so that you've got a column with the units, and a column with the tens, and a column with the hundreds, and so on. And then you go through these, you add up the units, and maybe it overflows over 10, and if it does, you have to carry something, and maybe not, so you just write down what results. And then you do the next column, and then the next column, and then the next column. And each column, you're adding up at most 3 single-digit numbers. So this is a bounded sort of problem. The adding of the single-digit numbers is something that is fixed. And then the amount of effort you have to do is determined by the amount of columns you have. So basically, the amount of effort you have to put in, either as a primary school child doing your homework, or as a computer implementing this, scales with the number of digits in your number. The more digits you have, the more work you have to do. If you double the number of digits, you double the number of work you have to do. So this is the computational complexity of adding, essentially. It is linear with the number of digits in your number. And you might want to count your resources in terms of how many times you need to use a transistor, or how many times you need to use a NAND gate, or or how annoyed your primary school child gets by having to do this. So there's different ways you can count the resources. So we don't usually in complexity theory have a specific number saying how much you have in terms of resources, but you just say what the scaling is. So this is why we say it's ON. It scales with n, the length of the numbers. For different mathematical problems, things are different. So here's a mathematical problem called factorizing, or factorization. And this means that for any number you might be given, we're not just going to be talking about numbers and maths the whole time, don't worry. For any number you might be given, there's a unique way to write this as a product of prime numbers. So for example, 2 is 2, that's an easy one. 4 is 2 times 2, so 2 being the prime number. 6 is 2 times 3, so this is the way you write it in terms of the prime numbers 2 and 3. 15 is 5 times 3, and so on. For any number, you can write it as a product of prime numbers, and that is unique. There's a unique sort of description of that number. Now you can then ask, if I give you a number, I can ask you, what are the prime factors of that number? And in some cases it's easy. If you've got a power of 2, you can very quickly verify it's a power of 2, and you can just say, oh, it's a whole bunch of 2's. If it's a prime number itself, you can very easily verify this. But for arbitrary numbers, there's no quick way of doing it, and you have to go into some complicated algorithm. And it turns out that the amount of computational resources you need to factorize an n-digit number increases exponentially with n, or at least the best algorithms we've ever known. And if we find ones that are significantly more efficient than that, then it collapses a whole bunch of computer science things, and some people would be very happy, but banks would be very unhappy because it's the basis of all cryptography. So for example, as a concrete example, not to just talk about complexity theory, a few years ago someone took this number, which is 2 to the power of 1061 minus 1, and factorized it. And that took 300 CPU years to factorize. The process of working out what its 5 prime factors were took 300 CPU years, and I think it took about a year of real time using a supercomputer. So this is really hard to do. But they worked out that it was that prime number times that prime number. And these are so long that they don't even fit on the screen, but nevertheless, they exist. And yet, if you were to go the other way, so I copy and pasted these numbers onto this online calculator, because my phone calculator would not take numbers that long. And I pressed go, and the amount of time it took to multiply them was like, well, a blink of an eye. I didn't even have to wait. And Wolfram Alpha often complains about being given problems that are too hard. It didn't complain, it just did it. So the computational problem of taking that number and working out what its prime factors are took 300 CPU years, but the opposite problem of taking those numbers and multiplying them together just took no time at all. So these are the kind of things that if you analyze the complexity of problems, these are the kind of things that you run into. There are some problems that are just too hard, and there are some problems that are very easy. And in games, this is something very relevant, because games are kind of a unique application of computers in which you have to do lots of stuff. It's not you just add or you just multiply. You have to do an incredibly huge number of different processes, and so you're going to very easily decide, I need to do such and such, and find out that it's something that takes far too long. And also games are an application that needs things to be fast, because you want to deliver a nice, pleasurable experience to the player, and the player doesn't want to say, let me move one step that way, and then your computer say, okay, great, just give me a day and I'll work out what it looks like. You need things to have fast feedback. So even something that a computer scientist might call efficient might not be efficient enough. So for example, doing 1 divided by the square root of a number is something that doesn't take that long. A computer scientist would probably say that's an efficient thing to do. But in Quake-free arena, they had to do a lot of it in a very short space of time to render the graphics. And it was too slow. It was too slow to be able to nicely render this graphic. So there was a method that was used in Quake-free arena called the fast inverse square root, which is a really weird hack that somehow gives you pretty much the same answer using maths magic. So that's an example of where you really have to get around the problem of computational complexity. Also in game design, the complexity of things like a puzzle or a level can also be measured, and that's relevant if you're also when you're generating a puzzle or a level that you want to actually be solvable. So the computational complexity of generating a random puzzle might be quite easy because you just put random stuff everywhere, but you want a level or a puzzle that you can actually solve, and the computational complexity of doing that will depend on how you do it, because you might make it like very easy and then just put a bit of random stuff that you know won't affect the solvability, but then that's going to be a bit of a rubbish level probably. So you're going to run into difficulties in how sophisticated you want to do this, and also how much time you have to verify that this is actually solvable. So as a place you can look for more information on this kind of thing, there's a paper from a few years ago called Classic Nintendo Games Are Computationally Hard, where people look at Super Mario Brothers, the first two Zelda games, Donkey Kong Country and Metroid, and analyze basically the computational complexity of these games. And they show that basic elements that you have within these games can give you levels that are very hard to solve the decision problem, which is this possible to be solved? Is it possible to solve this level or not? And so this is a figure from that paper, and as you can probably recognize if you've played some early top-down Zelda games, this is one of the block-pushing puzzles where you have to push some blocks and you can only push them once, and you have to get from one place to another. And this is the kind of thing that can very easily run into complexity problems if it's too big. If you imagine, so usually you've only got a few blocks when you have to do one of these in an actual game. If you imagine one of these that's 1,000 by 1,000 blocks, then how do you solve that? It's going to become very hard very quickly. So also someone in the questions talked about ray tracing. Well, I can't say too much about that, but I have got a screenshot here from the Wikipedia article on ray tracing, which has a section on computational complexity. And you can find that it's quite an interesting problem from a computational complexity perspective, because you've got these decisions. So you've got these problems where you can ask, if I have a ray that starts at a certain point and goes in a certain direction and interacts with the surface, will it end up at a certain point or not? So this is the kind of minimum thing you need to know when you're ray tracing, because you want to know where that ray is going to go. So asking whether it will end up somewhere or not is kind of important. And a lot of these are undecidable problems. So this is kind of the hardest problem you could ever have, because it's impossible. It is impossible to write a program that can solve an undecidable problem, because that would just break logic. So this is not something even you can throw a lot of computational resources at. It's just impossible. And that depends on the nature of the surface that you're trying to do ray tracing on. So you can very easily, in ray tracing, run into problems of undecidability. So any program that you write is either going to be wrong some of the time, or it's going to run forever, which obviously you don't want. Also, you have, for things that are possible, depending on your surface, you can get things that are p-space or p-space hard, which might be something, coming at it from quantum computing, we often look at something like p-space and say, oh, that's all right, that's pretty efficient. But actually, these can be problems that take quite a lot of time. and that depends on your surface. So because of your computational complexity, you're bounded on what sort of surfaces you might want to have in your game, because otherwise it's gonna be either a problem that takes too long to run, or it runs into undecidability, which is really not a very good thing to have. Also, I'm going to give you an example based on the traveling salesman problem. So maybe you want to make a game based on the traveling salesman problem. I mean, who wouldn't? In fact, there is a game, I think Mathematica, which is a package for doing maths, uses itself as a game engine for a version of a traveling salesman based problem. But anyway, I'll tell you what the problem is in case you don't know. Basically, you set a bunch of points, and you can imagine these are cities, and there's some cost to move between them. So this might be just the distance, or it might be the amount of time it takes on the train, or it might be the amount it costs, or whatever. Some sort of measure of cost, and you've got a traveling salesman who needs to travel from one to the other, and wants to do it in the most optimal way possible. So how do you find a path that connects all of these places in the most optimal way? And this is something that's computationally hard to do. The runtime of doing this is long. This is not an easy problem to solve. So it makes a nice puzzle. You could set a bunch of points. You could ask the player, what's the best route you can find? And then the player will come up with a route. And then the player is going to want some feedback, because the player is going to submit a solution, and it's going to expect you to say, yeah, or that's not a very good one, try again. You're expecting to get, like, is this a 1-star solution, or is this a 3-star solution? So you need some feedback as a player on what's going on. But if the computer itself cannot work out what the most optimal solution is, you're limited in how well you can offer that feedback. So you want the computer to know the solution to this puzzle, so you can say, okay, you've got a solution, it's a good solution, it's not the best solution though, so you can move on, but you can try and do better. So you're running into computational complexity issues there, where you don't know necessarily how much to give feedback. So on the Mathematica version of this, which is of course not probably the best example of game design, they run their own approximate algorithm, which gets a pretty good guess of what the best solution is and gives you feedback based on that. But in general, that's not optimal, and you might want something better. So in terms of puzzles that are computationally hard to solve, or levels that are computationally hard to solve, you might run into issues on telling a player how good their solution was. So another hard problem is simulating quantum physics, and this is something that is has some relevance maybe to game design, but is more a problem in physics, because we want to be able to simulate quantum systems. So molecules are quantum systems, and the interaction of molecules, that is also quantum. And we're currently at the level where we're designing drugs and we're designing materials at the sort of molecular level. So being able to really understand what's going on at that level would help us in so many different technologies, but we can't, because computationally it's a very hard problem. So explicitly, if you have n interacting quantum objects, whatever that means, I won't give you a lecture in quantum physics, the computational complexity is exponential with n. So for 1, it's easy. For 2, that's all right. For 3, might be getting a bit hard now. But for caffeine, which is a fairly big molecule, then you're getting quite hard there. So fortunately, caffeine already works, but maybe there's a better caffeine. We just don't know how to design it. So one thing that we can notice from this is that quantum objects simulate themselves fine, even though we might not be able to unlock all the secrets of caffeine because it's computationally hard. Caffeine works, you know? Your morning cup of coffee, it does the job. So somehow, nature is able to work out what quantum systems can do, even though we, with our computers, cannot. So that gives us a little bit of hope, because if nature is doing it, then we can just construct whatever it is we're interested in, and then look at it, and then we'll know what happens. You know, if we're interested in a certain arrangement of quantum objects interacting in a certain way, we could just build it and then look at it, and then we don't need to do computation. However, that would be quite a hard thing to do, because making things at the molecular level is, you know, not that easy. So what we really want is something that works at the quantum level, is made up of some sort of quantum object, but which is reprogrammable and very easy for us to change how it's designed, and also for us to look at, for us to observe what's going on inside of it. So basically we want a reprogrammable quantum thing, and then we can just prod it to becoming whatever it is we're interested in, and then we can look at that, and then we can get some, we can get an idea of what these quantum systems are doing. So what we're basically doing there is we're asking for a new kind of computer, or a new kind of simulator at least. And this simulator will do something that is too hard for normal computers. So we found a kind of, it is essentially an information theoretic device that is doing something that is impossible for the kind of computers that we have, or at least is very inefficient for the computers that we have. So yeah, that's the idea, and we have built it. So at IBM, we're building it using small loops of superconductor, essentially, which are then cooled down to almost absolute zero, and these behave as quantum objects. And we can address these with little pulses of microwaves, and we can make them be whatever it is we want them to be. We can make them simulate whatever we want to simulate. And someone asked, how does a quantum computer store information? Well, I'm not going to give you too much of a lecture on physics, but basically, when you look at the quantum level, the amount of energy an object can have does not vary continuously as it appears to do on our sort of scale, but there's very discrete amounts of energy something can have. So it can you can have something oscillating at a low level, but then you can't just make it oscillate a little tiny bit more. You have to make it jump up to oscillating to a higher level, and then to another higher level. So you have these jumps in the amount of energy that it can have. And we just basically isolate these two lowest energy states, and we call one of them 0, and we call the other one 1. And it's like a bit, but it's at the quantum scale, so it's going to behave in a quantum way. And we're going to be able to use it as this quantum object, which is the fundamental unit of how we're going to build, for example, simulations. But the important thing to note is it isn't just a simulator. So I'm telling you this story because it kind of follows the way that we historically developed quantum computing, because there were these ideas at first, oh, it's hard to simulate quantum systems. Quantum systems simulate themselves fine. Let's build a quantum device that does this simulation. But then over time, people began to realize, well, just as a normal computer was built to do maths, and we can do games and Facebook and whatever with it, a quantum computer was initially envisioned to do simulation, but we can also do whatever we want with it as well. So it offers us a new paradigm for computing, which is different from the paradigm of standard computers. And in fact, for example, you can do a NAND gate using quantum computers. And so you can take any program that you've written for a normal computer, you can compile it down to NAND gates, and then you can rewrite this in terms of a quantum computer. So a quantum computer can run any program for normal computers, but it can also do things in a fundamentally different way. So yeah, we found that, for example, factoring, which is what I was talking about earlier, can be done much, much faster on a quantum computer. Search algorithms, if you want to search a database using a classical computer, then you basically, so if you want to sort of, if you have a phone book maybe people here are too young to know what a phone book is, but it was this book where it had people's names and then their phone numbers. If you want to know the phone number for a certain person, then that is very fast to search because it's listed, alphabetized by person, so you basically know where in the directory to look for that phone number. But if you have a phone number and you want to know whose phone number that is, then you've basically got to go through the whole phone book. Is that the number? No. Is that one? No. Is that one? No. And it's a painful process. It scales with the number of entries in the phone book, which is usually quite a lot. But we have in quantum computing a way to do it that scales with the square root of the number of entries, which still is not an exponential speed up, but it is quite a good speed up. Also, optimization problems we can do faster on a quantum computer. And often, if you're solving a puzzle or you're solving a level in a game, you're trying to solve an optimization problem. What is the optimal way to get from the start to the end? So there's hope that quantum computers can work out the optimal solution much better than normal computers. And then, for example, in the traveling salesman problem, it could tell you the optimal solution, so you could use that in the feedback that you're giving to your player. Another thing is random number generation. So if you're happy with current random number generating algorithms, then it's not going to be too much of an advantage in using a quantum computer. But any random number generation algorithms we have at the moment aren't really random. They're actually working on things that are predictable. So you may get artifacts in your random numbers. You may get random numbers that aren't very good quality, and then you have to look for better random numbers because they're causing weird things to happen in your game. Whereas quantum computers can generate genuine random numbers. When it gives you a random 0 or a 1, then it is the universe has given you something that is completely random and completely unpredictable. So that's another good use of quantum computers. We don't have to do fancy things to try and get good quality random numbers. We can just pull them out of the quantum computer. Now, someone asked, will we be able to instruct a quantum computer by writing code as if we were doing that with a regular computer and make a game, for example? And the answer to that is yes, and in fact, I've already tried that out. So in terms of writing code, we already have frameworks created over the last few years where you can write code essentially in Python in order to control one of the real quantum devices that are currently available. So this is an example of a quantum program here. We're setting up one quantum bit, and we're setting up a normal bit where we're going to put our output, and then we do a certain operation on that, which I'm not going to go into the details of, and then we extract the output. And in terms of making a game, well, this is actually a snippet from a game. So a few years ago, I wondered, can I make a game for a quantum computer? And I had a few experiments, which I've now retconned as not being the first quantum games. They're just early experiments. And then eventually I came upon making a version of battleships for a quantum computer. So in this version, well, I'll talk more about it later, but it's basically you're using the 0 and 1 states of your quantum bit as a battleship that is either intact or destroyed, and you're using certain quantum operations to be able to go slowly from 0 to 1. And so it takes a few hits to destroy one of your ships. So there's a blog post on Medium I've got called How to Program a Quantum Computer. It should be Googleable from that. And yeah, it explains part of the reason for making this was to help people understand what it is to make what it is to program a quantum computer and what a quantum computer is by having a small, simple, and relatable example. Someone else asked, this type of computing should probably require some new type of interfaces and developing methods for software and applications. How do you see these developing in the coming years? Well, because I work for IBM, I have to kind of say IBM are doing it, and IBM stuff is best, so just go for that. But basically, we've got this thing called Qiskit. This is a Python framework that you can use to construct programs for quantum computers. And so we have it at the most basic level, where you're actually saying, I want this qubit, and I want this qubit doing that, and I want this qubit doing that. So you're really, it's sort of at the level of writing programs in terms of NAND gates. You're really addressing it at the hardware level. But also we have higher level applications. So if you want to do machine learning or optimization, you can use pre-existing tools. So you don't have to go down to the bottom level. And I think this is how it's going to look in general. People are going to be making better and better tools to write at the machine code level, and better tools that operate above the machine code level. And probably in the early days, this is going to focus on things like trying to solve problems in quantum chemistry. So this would be related to the simulation that I talked about earlier, but also things like optimization and search, which you may be able to build into a game, should you wish. And they're mostly Python-based. So if you like Python, then that's good, and if you don't, then that's bad. Okay, this is probably a slide that should have been earlier, but just to justify how quantum computers differ from normal computers. Normal computers, we can think of the NAND as the basic atom, the building block of any program, and how many NANDs you need is essentially how complex that problem is. But you can do NANDs in quantum computers too. So anything you can do on a normal computer, you can do with exactly the same complexity in a quantum computer. But you can also do what's essentially half of a NAND. So something that you need to do twice to get a NAND, but if you do it once, you have something that's not a NAND. Or you can do a third of a NAND, or any percentage you want of a NAND. So it's like we're not just stuck with this building block that we had for normal computers, but we can chop them down, we can remold them. We have things that are more adaptable. So using a normal computer is kind of like building things in normal Lego, where everything's a bit blocky. Lego's great, but everything's a bit blocky. Whereas using a quantum computer is kind of like using Lego Technic, where you can make things far more sophisticated and moving parts and everything. So if you want to have any idea of what a quantum computer is and how it relates to a normal computer, then think Optimus Prime. And as I said earlier, we have many algorithms, many examples of algorithms that we know that can be run on a quantum computer, but most of these have been focused on things that have good speed-up proofs. So not really focusing on what people who maybe work in maths departments and who are thinking about quantum algorithms aren't sitting there thinking, well, when there is the first set of clients for a quantum computer, I wonder what they'll want. Let me design an algorithm for that. They've been thinking, let me design an algorithm that has a nice mathematical proof of how good it is and how much it improves over normal computers. So most of the algorithms we have relate to that. And most of them, even so, we can think of how to incorporate them into things like gaming. But if we really want to use them for any purpose, then we have to start thinking about those specific purposes in the near future. Okay, so what could we use quantum computers for in gaming? So here's one simple example. Physics lies at the heart of many games, like Portal, or even Angry Birds. Angry Birds is just trajectories of particles with a constant initial velocity in a gravitational field. You don't think of that when you play it, but that's exactly what you would calculate in your first year course doing a physics degree, is exactly what's going on in the game engine of Angry Birds. And this is actually a screenshot from something called Quantum Cats, which is kind of a quantum Angry Birds, which you can check out if you want. Yeah, this means that with quantum computers, we could allow for games based on quantum physics. So currently, there are already games that are based on quantum physics, but they take some small easily simulable part of quantum physics. But with the ability to simulate large-scale quantum systems, it will open us to lots of new game mechanics that we might want to try out. Another thing is that we could use them for graphics. So searching databases is a significant part of rendering graphics. And so exactly like looking up, you need to know who has a specific phone number. You need to do problems like that when you're rendering graphics. And because quantum algorithms can do that faster, then this could be an important part of rendering graphics. There's also other ways that we could try, because rendering graphics is quite a large set of computational problems, so there are other ways that we can pick out things from the quantum algorithm zoo, which is this list of all the known quantum algorithms, and try and see how to work them into our algorithms for rendering graphics. So there's a few papers by a professor called Simona Karaman, I think. And there's also a recent startup called Boxcat, whose URL is Boxcat, but with a dot between the C and the A, as if it's an Austrian URL. So these are people that have looked at this problem. Now, I'm not really familiar with that so much because this is not something that people have really looked at too much. It's not something that's really been the focus of research into quantum algorithms. But if you want to see examples, then there are a few at least that I can point you towards. But one thing I would say about both of those things, about using quantum physics to generate your game mechanic and using quantum physics to render your graphics, is that what they will require is the quantum computing to be within the game loop. So within this constant loop of getting user feedback, you would get some user feedback and you would use that to formulate a new job for your quantum computer, and then the results from that you would give back to the player and so on. So that means that if your PC could have a quantum card that it slots in next to the graphics card, then fair enough. That would be feasible. However, quantum computer hardware is not going to be like this. So for example, at IBM hardware, this is a lab in which a few devices exist. So I think you can see about 2 devices in there, and this does not look like 2 graphics cards, as you can see. It looks like a whole room, and it's got people in and a lot of wires. So basically, the techniques that we use to reduce noise are very big and expensive. So for example, you have to cool the devices to almost absolute 0, and you need quite a large device to get those sorts of temperatures. So the current model is of a cloud-based service, and of course we do have games which operate over the cloud. So for example, massively multiplier games do have to rely on the cloud within the game loop. So we could imagine one day there'll be enough quantum devices that we can indeed use some time on those devices, incorporate it into quantum computing into the game loop. However, in the near future, where demand will outstrip supply, if you want to have a game that's got 1 million players, there are not 1 million devices to run it on, even if they're each using one, and the time it takes to send a job is not the kind of time scale that you would want if you're rendering graphics. So in the short term, it's best to consider quantum computing not inside the game loop. We have to move it out of the game loop and then find applications for it elsewhere. So for example, if you're using quantum computing for optimization, then you can generate a bunch of puzzles and work out what the best solution is and work out how to give feedback to the player. For example, in our traveling salesman problem, you can generate a load of traveling salesman problems. You can use the quantum computer to work out the optimal solution. You can then bake that optimal solution into your game and then ship it, and then the quantum computing happened in the design stage. It doesn't happen while the game is running. Or you can have it during a loading screen, so you could procedurally generate a new puzzle, and then while you're loading, you're using the quantum computer to work out the best solution for that. But you're not having it within the game loop. So similarly, you can easily determine whether a random level that you've generated is possible to beat. So if you're randomly generating one of these Zelda puzzles, you can maybe run it on a quantum computer to see if that level is beatable, and if it is, you know you can give it to the player and you're not giving them something impossible to do. And of course, this is a problem in procedural generation at the moment. You can randomly generate content. You need it to be beatable, and so often what this means is that there are limitations to how the randomly generated content is made to ensure that it can be beaten. But this sort of cripples your ability to do random generation in a scale, in a way that is as flexible as you might want. So it'll just increase your ability to find new ways of randomly generating levels, because you will increase your ability to be able to do this verification step of working out whether you can actually beat the level or not. So in this case, the quantum computing is used maybe in the design stage or during a loading screen, and therefore is not intrinsically in the game loop. It's somewhere that the player is happy to wait for a little while. And also you can produce truly random numbers more easily. Removes the need to rely on pseudo-random numbers. So this is something where you can pull a bunch of random numbers out of the quantum computer during a loading screen and then use it in the next level, depending on what your application is. Another thing, so when I talk to game developers about quantum computing, one thing they often want to know about is graphics. So I've talked about graphics a little bit, and as I said, it's not something that has been actively developed, so there's room for more work to be done on how you can use graphics, but it's probably not something you're going to do in the next few years on a quantum computer. Well, at least not within a game where it has to be in the game loop. Pre-rendered graphics might be a completely different thing. Another thing that people are quite interested about is quantum computing for AI. So AI for quantum computing is also something that is an active area of research at the moment. So people are doing some interesting things in this. And you could use a quantum computer for enhanced AI during your game. And then this isn't necessarily in the game loop either, because it might be during your wait for another turn. I play a lot of Civ 6 at the moment, and I'm used to having to wait for a little while in the middle of my game because the other players are having a turn. So this is somewhere you could also use quantum computing. Pertaining to AI, someone asked basically if we could make brains in a quantum computer that have true emotions or feelings. And well, in theory it's possible. So if you ask me the same question about something of a similar size and complexity to a brain, such as a bowl of soup, and there's crazy weird stuff going on in the bowl of soup as well. Turbulence is a very tricky problem. So in theory, you could, a bowl of soup is just a quantum system, and you could simulate that quantum system on a quantum computer. Or if you ask me about a piece of cheese or whatever, I would say, yeah, sure, you can do that. But a brain, well, there are philosophical implications to that I don't want to get into. So I guess so, but yeah. That would also require a very large quantum computer. So let's go more for a quantum version of Watson beating Jeopardy rather than trying to come up with Lieutenant Commander data for now. Okay, so this was the first part, what quantum computing might do in the long term. So inside the game loop, we might use it for quantum physics simulations and for graphics rendering. But in the shorter term, so it's still in the medium to long term, outside the game loop, we can use it for optimization-based tasks, procedural generation, AI. We can also use it, I didn't have a slide on this, but we could also use it for developing new game mechanics, where we use the quantum computer to prototype out the game mechanic, but then find a way to do it more more efficiently such that it can just run on a normal computer and doesn't actually need to rely on the quantum computer. So you use your simulation to prototype a new type of game, but then you take the basic essence of that, because when you're making a game, basically you want it to be fun for the user. You don't necessarily have to have it purely scientifically accurate. So you can abstract out what is fun about that game, what is engaging about that game, and then re-implement it in a way that's more efficient. Okay, so in the second part of this lecture, I will talk about quantum computers of today and how we might use those for games, or why we might use those for games. So this is something that you can go home tonight and do. So someone did ask, aside from speeding up processes, are there any bridges we can cross now using quantum computers for games? So this is basically what the second part is about. But I would like to say this is not something that people have done a lot of. This is something that people are quite interested in, so it's within the last few years people are starting to look into this problem of using quantum computers for games, especially in the near term. But there's not been a lot of it, so it's really something that you can be a pioneer of. So yes, I think there are many bridges we can cross, but most of them we don't know where they are, and we have to go and find them. Okay, so let's talk about what it means to be, or what the characteristic features are of near-term quantum devices that will form the design problem of how to design games for them, and also tell us why we might want to do it. So current devices are what we might call small. So for example, this is a 16-qubit device. So a qubit is the basic building block of quantum computers. It's like the bit in a normal device. So this is a 16-qubit device. And if you were to go back 5 years and say to someone that a 16-qubit device was small, they would probably, well, they'd think you were a theorist, which to be honest I am. Because at that time there was only 1 or 2 qubits, and having 2 qubits interacting nicely was a pretty big step back then. So in terms of experimental physics, these are huge devices. This is an achievement like building CERN or something. But in terms of being a computer, they are quite small. There's not much computation you can do on a 16-qubit device, and you can simulate them quite easily, because then you've not yet reached the point where the exponential cost of simulation causes it to be too hard. So current devices are, from a computational standpoint, quite small. You'll need 50 to 100, something like that, in order to do something that standard digital computers cannot do. And with current devices that are available for the public, there are no more than 14 qubits available. Another aspect is that current devices are noisy. So at a very basic level, you can take a qubit and you can set it to be 0, and then you can look at it and say, what are you, 0 or 1? And it should say 0, obviously. Or you can set it to be 1, and you can ask it, are you 0 or a 1? And it should tell you 1. But because of the noise, you can set it to be a 0 and ask it, are you a 0 or a 1? And with some probability, it will say that it's a 1. So it will lie to you sometimes. So this is one of the fundamental problems. Qubits at the moment lie. Qubits at the moment talk to each other when they shouldn't. They're like misbehaving school children, and we've got to make them behave a bit better. So for example, this is from a program where I make it that the neighboring numbers on the big dots here should, well, what am I saying? You should be able to, this is a puzzle basically, and you should be able to go looking at the big dots and find pairs of big dots where the 2 neighboring big dots have the same number. So for example, there's a 54 and a 58 there. They're almost the same, so there's one of your pairs. But if you were to work through this, it's kind of hard to work out where these pairs are, because of the noise is causing them to be a little bit more random than they should be. So they're misbehaving, as I said. So we have to find new ways of designing programs and processing readouts to mitigate for this in the short term. And for the long term, we'll also have to come up with schemes for error correction, which will basically get rid of all of these errors completely. So when we are making applications in the near term, we have to think about noise, and we have to work out what we're going to do with noise. Although for games, you can incorporate the noise, and then it can be a feature rather than a bug. So what we're going to do with quantum games that are in this era of devices that aren't necessarily that big and which are relatively noisy. Well, one thing we could do is make them part of citizen science projects, or we could use them to help a wider audience understand the devices. So for example, this is just a figure, I'm not really explaining it too much here, but the game this is from is basically a very simple puzzle game which is designed mostly to let people have some idea of what the current devices look like and about the noise processes on current devices. Also, a few years ago, before I joined IBM, I made an app called Dikidoku, which was a citizen science project, which basically took problems from my own research in quantum error correction for quantum computers and presented them in a way that the public would be able, so anyone would be able to tackle. So people could try solving the problems in my own research. And I did this in a way that was simulated. It's a particular problem that can be simulated quite easily. But also you could then have this, but not simulated. You could take real examples of noisy devices and make problems out of those and give them to people. And then people can start to understand what it is to do error mitigation. And maybe even as part of the game, design better error mitigation methods to design better error mitigation methods than we scientists have done, or at least to inspire new directions for scientists to look into. So that's one example. Making games for the glory of science is something we can do with near-term devices. And so one question was, could simulation games be improved so much that they would reflect reality so closely you could actually make some scientific discoveries just like by playing? And I think that's definitely the case. So with Dikidoku, which is my game, or if you look at Quantum Moves, which is, or any of the other games made by Science at Home in Denmark, then they take parts of quantum physics that can be simulated quickly enough to actually be part of a modern game, and then allow people to play that, and by playing that, get insights that can be used for actual science. So people are making scientific discoveries by playing these games. And if we don't have to restrict ourselves to these tiny corners of quantum physics where things can be efficiently simulatable, but we can do any quantum physics, then we have broadened our scope for being able to present interesting physics to people as game mechanics and allowing them to make discoveries. Because when someone plays a game, then they are basically learning the universe that the game creates. The game creates this new universe. It has its own rules. People are learning basically the laws of physics of this universe, and they're learning how to use those to do whatever it is that is the aim of the game. And of course, that's even more exciting when there are glitches in the game, because these are particularly nice little bits of physics, almost like magic, where you can magic yourself straight to Ganon and beat Ocarina of Time in 15 minutes or whatever. So people, it's like often the way gamers, or at least very dedicated gamers, and especially say speedrunners, approach a game is with a very scientific outlook. They are being scientists of that universe. And so you can harness that to make a game based on real science, and then they're actually learning about the real universe. They're finding ways to speedrun the real universe, which is effectively what technology is all about. And also quantum computing can be used for inspiration. So a lot of sci-fi is based on ideas from quantum mechanics, and maybe those are not necessarily very informed ideas from quantum mechanics. So if it is true that one application of the quantum realm is it helps you defeat Thanos, then the actual quantum going on in that is not going to be real science. So sorry to spoiler the next Avengers film for you, but don't take that as real science if Ant-Man and the Wasp is anything to go by. But we could use quantum computers to prototype new game mechanics. So even with just small numbers of qubits, you can get a feel. You can actually have like a tactile experience with quantum systems, and you can start to see what is different about the quantum objects, about qubits, that isn't true about bits, and then these might inspire new ideas for game mechanics for you. And so this is an example of quantum computing used during the design stage, so that's also not in the game loop. Another example, you could have quantum computing that creates a genuine sci-fi experience. So here's an example that has nothing to do with IBM or me, but I found on the web. It's called Universe Splitter, and it's an app. It's basically a coin flip app. So what is more boring than a coin flip app? You just get an app where you say, shall I have a pizza or shall I have a burger? And it randomly tells you one or the other. I mean, why would you even need that app? You could just flip a coin. But it takes this and it implements it in a really nice way, because for one thing, it's using a quantum random number generator, which is made by a quantum cryptography company. So this uses the cloud. It asks the quantum random number generator, give me a random bit, and the random number generator gives a result. And it uses this idea that there's this thing called the many worlds interpretation of quantum mechanics, which basically says that every time you ask a quantum computer to do a random thing, then it splits off into two universes, one in which one thing happens and one in which the other things happen. So this app is basically something which is magnifying that effect. It asks a photon, what is your polarization? And we split in these two universes, and in one universe you have pizza, and in the other universe you have a burger. So that is what it's taking. It's a coin flip app, but it's selling itself as something which splits the universe every time you want to make a decision. And it has these little, there's a chart tab where it shows how the universe you're in has split off from all of the other universes. Oh yeah, look, there's the one where I decided not to have a salad all the way back then, and that's why I'm choosing between a burger and a pizza today. So it's a really nice way of taking, it's basically a very boring thing, but because it's implemented using quantum technology, it can build this narrative around the fact that it's really using this quantum technology, and it makes it something that's quite interesting. And it's like a App Store staff favorite, I think it was. So you can use that also in your games. There's a lot of games based on sci-fi, and the fact that you're using real quantum technology maybe it's not something, it's something that you could simulate. So in terms of actual implementing your game, you don't need it, but you can also think about what feeling it gives to the player when they're playing it, and that psychologically they might like the fact that they're actually using or misusing a real quantum device by playing the game. So one thing that someone asked was, what kind of challenges will there be for artists in game development for quantum computers? And I think there's probably many challenges, but one that really strikes me is something that was relevant when I was making a game. So before I joined IBM, I was collaborating with IBM on making this app called Hello Quantum, which is a game which is based around quantum computing. And so we wanted it to be that someone could basically, in this game, program a quantum computer. They could see the quantum computer reacting to their program. But one problem is that there's a lot going on inside a quantum computer. In order to efficiently be able to do these highly complex algorithms, that means that qubits themselves are quite complex.